Linear wave shaping circuits. Before discussing linear wave shaping circuits in detail, let us first define what are wave shaping circuits. Suppose we have a particular kind of wave. It may be a sinusoidal wave or a square wave or rectangular wave or a pulse, and we wish to change the shape of that particular wave. Then we can make use of some specific circuits. In these circuits, if we apply a wave as the input signal, then the property of the circuit is that it changes the shape of the wave. Such circuits which change the shape of a particular wave applied to these circuits as the input signal are known as wave shaping circuits. Now the wave shaping circuits can be categorized into linear wave shaping circuit and non-linear wave shaping circuit. Before categorizing them or before studying them as wave shaping circuits, let us recall what are linear circuits and what are non-linear circuits. We know that the linear circuits are those in which the variation of current and voltage or the relationship between voltage and current is of linear nature, or in other words, the current is directly proportional to voltage, or the voltage, or we can say potential difference, is directly proportional to the current flowing through the circuit. These circuits are known as linear circuits. The basic property is that if the circuit parameters like resistance, inductance or capacitance in a circuit remains constant independent of the applied voltage or the current flowing through the circuit, then the circuit behaves as the linear circuit. So a simple resistor or an inductor or a capacitor are the examples of linear circuits. Nonlinear circuits are those circuits in which the circuit parameters like resistance, inductance and capacitance do not remain constant and they vary with the variation in the applied voltage or the current through the circuit. Then they are known as nonlinear circuits. And the examples of nonlinear circuits are diode, transformer, iron core, transistor, etc. And for these circuits, the relationship between current flowing and the applied voltage is not linear, but it is non-linear. Now let us see if a sinusoidal wave is applied to a linear circuit which we have defined a few minutes earlier. When a sinusoidal wave is applied to a linear circuit, then it does not change its shape. Means that the output wave will also be of sinusoidal nature. The only difference is that the amplitude of the wave will be changed, or the power contained inside the wave will be changed, or we can say that some phase shift will be introduced in the wave, but the shape of the wave will remain the same. Now we are studying a linear circuit, and at the input a non-sinusoidal wave is applied. As we will see later in further slides, we can observe that in this case the shape of the output wave will be different from the shape of the input wave. So when non-sinusoidal wave, for example ramp or rectangular or a square wave is being applied to the input of a linear circuit, then the shape of the output wave will no longer be the same as the shape of the input signal. And if we consider non-linear circuit, then in these circuits, if a wave of any shape, be it sinusoidal or any other kind of wave is applied to the input of non-linear circuits, then it is found that the shape of the output wave will be compulsorily different from the shape of the input signal. So this is the difference between the wave shaping of a linear circuit and in the wave shaping of non-linear circuit. Now we will concentrate upon the wave shaping by linear circuits. The first example of a linear circuit which we will discuss in detail is a high-pass RC circuit. In the forthcoming slide, we have shown the circuit of a high-pass RC filter or RC circuit. As the name suggests, a high-pass RC circuit consists of a resistor R and the capacitor C, and the main or important thing is that in this case the output is taken across the resistor. We will see in the forthcoming slide that a current is flowing through this RC circuit and the output is taken across the resistor, or the output voltage is the potential drop across the resistor. In this figure, the circuit of high pass RC circuit is shown. As we can see, this is a capacitor and this is a resistor. Current I is flowing through the circuit. When we apply the input signal Vi, and when this current flows through the resistor R, then across the resistor a potential drop is produced, and this potential drop is taken as the output voltage. When this kind of combination or a system is developed, then it is known as high pass RC circuit. And as we have discussed earlier, this high pass RC circuit behaves as a linear wave shaping circuit. Now important thing we can discuss here, though we may be knowing it from our past study of electric circuits, why this type of circuit is called high pass RC circuit. We know that when an AC signal is being applied as the input signal to this circuit, then it has some frequency. Then the reactance of the capacitor is 1 upon omega C, where omega is the angular frequency of the signal. Suppose the frequency of the input signal is very low, that is omega is very low, then the capacitive reactance will be very high since it is appearing in the denominator. So the capacitive reactance will be very high for lower frequencies. So in these cases of lower frequencies, when the capacitive reactance is very high, so the most of the applied voltage will appear across the capacitive reactance as the potential drop, because the reactance is high. So the potential drop across the capacitor will be current multiplied by reactance multiplied by capacitive reactance. So if the capacitive reactance is high, then the potential drop will be very high. Naturally, the applied voltage is equal to potential drop across the capacitor plus the potential drop across the resistor. So it is obvious that when the a constant voltage is being applied and most part of it is appeared across the capacitor, then naturally the output voltage will be very low. And this is the case when the input frequency of input signal is very low. Hence, for low frequencies, the output voltage is very low. But when the frequency of applied signal is very high, that is omega is very high, then the capacitive reactance is very low. So in these cases, the potential drop produced across the capacitor will be very low. Hence, most of the applied signal or the voltage will appear across the resistor. Or in other words, we can say that for higher frequencies, the output voltage will be high. And when the frequency of the input signal is excessively large or excessively high, then this capacitive reactance is almost zero, or it behaves as a short circuit. It appears as if it is directly connected to the other part of the circuit. This is short circuit. So the whole voltage which is applied at the input will appear across the output resistor. Hence it is called high pass RC circuit, because it is smoothly passing the high frequency signal and it is blocking the low frequency signal. So this is the significance why it is called high pass circuit. Now let us see what is the response of this high pass RC circuit to the sinusoidal input. As we have discussed earlier, when a sinusoidal input is applied to a linear circuit, then it does not change its shape. So it is for sure that when we are applying sinusoidal input to the high pass RC circuit, which is a linear circuit, then the output signal will be a sinusoidal wave. This we will see in further forthcoming slides. Now suppose the input voltage in this case is represented by Vim sin omega t, where Vim is the amplitude and current in the circuit will be applied voltage upon impedance, and impedance of this circuit is resistance R plus capacitive reactance, which is 1 upon j omega c. So this is the current I flowing through this high pass RC circuit. As the current I is flowing through the RC circuit, the output voltage, which is the voltage taken across the resistor R, will be I multiplied by the resistance R, and I can be written as Vi upon the impedance. This is the value of I multiplied by R. Now we have made rearrangement in this equation, and after rearrangement it becomes like this. In place of Vi, we can write down the expression Vim sin omega t multiplied by 1 upon impedance of RC circuit, and it can be written as in the form of amplitude multiplied by sin omega t. It can be written as Vom sin omega t, where Vom is the amplitude of the output voltage. And the expression for Vom is written here. This is the amplitude of the output signal. So we can see from this expression what is the relationship between the amplitude of the output voltage and the amplitude of the input voltage. As we have discussed earlier, when a sinusoidal wave is applied to a high pass RC circuit or any other linear circuit, then the shape of the signal remains the same, because the input signal was Vim sin omega t and the output signal is Vom sin omega t. Both are sinusoidal, therefore there is no difference in the shape of the signal. The only difference is that the amplitude of the output signal is reduced by this factor. This is the amplitude of input signal, and when it is divided by this quantity, then it becomes the amplitude of the output signal. So this is the difference which the high pass RC circuit has introduced in the applied signal. Now we have made some mathematical rearrangements just to simplify this equation in order to discuss it in a simplified manner, and it comes out to be in this form. It is very easy to understand for the students of physics and maths. And uh, uh, any equation which is in the sinusoidal form can be split into two parts. This is the real part and this is the imaginary part, and by mistake in the imaginary part, this term, iota term or j term is were left by mistake. So it should be j at this point. This is so that the second term will be imaginary term, which is j vom sine theta, and this is the real part vom cos theta. So this is the general expression for the output wave, and this is the actual expression for the output wave. Now from the above equation, equating the imaginary and the real parts on both sides of the equation, we obtain the expression for vom cos theta and vom sin theta. And by squaring and adding these two quantities, we obtain the expression for vom. This is the magnitude of amplitude of the output voltage, which we obtain as Vim upon under root 1 plus 1 upon omega square r square c square. And by dividing the sine expression for vom sine theta by vom cos theta, we obtain the expression for tan theta, which is tan theta is equal to 1 upon omega rc, where theta is the phase change introduced by the RC circuit. So we can make out that there are two changes in the signal when it is applied to the high pass RC circuit. The first is that the amplitude of the wave is reduced by this factor, and the second is that the phase difference of theta is being introduced, where theta is equal to tan inverse 1 upon omega RC. And we know that in an RC circuit, the term RC is defined as the time constant, and we normally represent it by the term tau. So we can say that theta is equal to tan inverse 1 upon omega into tau, where tau is the time constant of the RC circuit. And if we calculate the ratio of output and input amplitudes, then from this equation it is 1 upon under root 1 plus 1 upon omega rc whole square. Now this is the ratio of two amplitudes, output amplitude and input amplitude, and tau is equal to rc is the time constant. In this equation, suppose we replace the quantity 1 upon omega rc by a constant term omega 1, because r and c are constant quantities for a particular circuit. Therefore omega 1 is a constant quantity, and we will replace 1 upon rc in this equation by omega 1. So the expression for vom upon vim, modulus of this expression, is equal to 1 upon under root 1 plus omega 1 upon omega whole square. Okay. Now come to this line of equation. Since omega is the angular frequency, so it can be written as 2 pi f1, and omega can be written as 2 pi f, where F is the frequency of the input signal and F1 is a constant quantity. What is the expression of F1? We can find out the expression of F1 by recalling that omega 1 we have taken as omega 1 is equal to 1 upon tau. Omega 1 can be written as 2 pi f1, which is equal to 1 upon tau, or 2 pi f1 is equal to 1 upon rc. Hence f1 is equal to 1 upon 2 pi rc. Hence we have obtained the expression for VOM upon VIM as 1 upon under root 1 plus F1 upon F whole square, where F is the frequency of the input signal that can be varied if we are varying the frequency of the input signal, and F1 is a constant quantity which is equal to 1 upon 2 pi RC, where R is the resistance used in the circuit and C is the capacitance of the capacitor of the RC circuit. Now we are in a position to discuss what is the exact effect of frequency on the output of high pass RC circuit. In the above equation which we have derived in the previous slide, if we impose a condition that the frequency of input voltage is equal to F1, that is, if the frequency of input signal is equal to 1 upon 2 pi RC, then in the expression for VO upon VIM, if we put this condition, then it comes out to be 1 upon under root 2, or it is 0.707. This quantity can be written as 70.7%. Or we can say that if the frequency of input signal is equal to 1 upon 2 pi RC, in that particular condition, the ratio of output voltage and the input voltage is 70.7%, or you can say in simple words, the output magnitude of the output amplitude is 70.7% of the input amplitude. Or in other words, we can say that the maximum value of VOM upon VIM is equal to 1, and if F is equal to F1, in that case the output amplitude is 70.7% of the maximum value. If we take the expression for tan theta, where theta is the phase difference introduced by the RC circuit, and tan theta is equal to 1 upon omega RC. Suppose the frequency of the input signal is very low, or omega is tending towards 0. In that case, when omega is 0, tan theta is equal to infinity, or theta is equal to 90 degree. So we can draw a conclusion that for lower frequencies, the phase difference introduced by the high pass RC circuit is 90 degree. And when the frequency is very high, that is, the angular frequency is tending towards infinity, and if omega is tending to infinity, then tan theta is equal to 0, or in that case the phase difference introduced by the high pass RC circuit is 0 degree, that is, the input and the output signal are in the same phase. Hence the general conclusion drawn from all this discussion is that when the frequency is very low, in that case the output signal is very weak, or the output voltage is very small, and the phase difference between the input voltage and the output voltage is 90 degree, and as the frequency is increasing, the amplitude of the output voltage is increasing continuously, and at excessively high values it is almost equal to the amplitude of the input signal, and the at very high frequencies the input voltage and the output voltage are in the same phase.